Hi everyone, let's move on. Again, what I'm trying to do here is to walk and work through the lab while you are watching, right? So you can do this in two ways. You can have a second screen, which would be amazing because then you can watch the video on one screen and work through your assignment in your iCloud account together. But if you don't have two screens, all good. You just have to be flipping back and forth between the YouTube tab, the tab that you're watching the video, and the tab that has the iCloud Studio and the documents that you can actually modify. Okay, so let's go. I'll put myself down here again, and we'll continue with the concept of functions. As we've seen, you can do quite a lot of calculations just by using the typical operators, plus, minus, the multiplication, the division, the power operator. However, in order to do more advanced calculations such that you don't have to type out the entire equations, we will use functions, right? So it's a compact way to do calculations. To get started, suppose I wanted to take the square root of 225. The square root is just the opposite of squaring a number. So for instance, since 5 squared is 25, I can say that 5 is the square root of 25. The usual notation for this is that little square root symbol that you all probably are familiar with, and it will show up in mathematical and statistical equations very frequently. Though sometimes it will also be written as like this, 225 raised to the power of 0.5. The second way of writing is kind of useful to remind you of the mathematical fact that square root of x is actually the same as raising x to the power of 0.05. Personally, I've never found this to be terribly meaningful psychologically, but it is quite convenient mathematically. Anyway, it's not important. What is important is that you remember what a square root is, since it's kind of useful in statistics. To calculate the square root of 25, I can do it in my head pretty easily since I memorized my multiplication tables when I was a kid. It gets harder when the numbers get bigger, and pretty much impossible if they're not whole numbers. This is where something like r comes in very handy. Let's say I wanted to calculate the square root of 225. There are two ways I could do this using r. Firstly, since the square root of 225, 225, there are some little typos here, is the same thing as raising 225 to the power of 0.5. I could use the power operator, the little hat, just like we did earlier. So it would be 225 raised to the power of 0.5. And that's 15. However, there's a second way of doing this. By using square root function, the function square root, like that. So let's use the function. To calculate the square root of 225, what's wrong with me, but it could be any number really, using the square root function, the command I type is this, square root of 225. So you have the function, and remember, all functions receive an input and provides you with an output. So if I run this little piece of code by clicking on the green arrow, I see the output. So I provided it with an input, it provides me with an output. See, it's the same as here. When we use a function to do something, we generally refer to this as calling the function. And the values that we type into the function, there can be more than one, are referred to the arguments of or inputs to the function. Obviously, the square root function doesn't really give us any new functionality since we already knew how to do square root calculations by using the power operator. However, there are lots of other functions in R. In fact, almost everything of interest that I will talk about in this class is an R function of some kind. One function that comes in handy quite often is the absolute value function. Compared to the square root function, it's extremely simple. It just converts negative numbers into positive numbers and leaves positive numbers alone. Calculating absolute number values in R is pretty easy since R provides the ABS function that you can use for this purpose. For instance, the absolute value of negative 13. So again, the function and the input, let's look at the output by clicking here, is 13. And then you may be thinking, oh my gosh, why do I need this for? Well, you can imagine if you have an Excel sheet, a data set with a bunch of scores, like laying in a column like this, and you just wanted to transform all of that in positive numbers, right? What do? You would have to go by hand and do each one of them. You see that with R, you can just use the abs function, and instead of using as input just one number, you can use a column of data. So you can do that pretty easy transformation in one little line of code instead of having to go into your data set and transforming everything. So that's one reason we use functions, to make our lives easier and really less prone to errors. Combining functions. Before moving on, it's worth noting that in the same way that R allows us to put multiple operations together into a longer command, like 1 + 2 × 4, it also lets us put functions together and even combine functions with operators if we so desire. For example, the following is a perfectly legitimate command. Square root of, open parenthesis, 1 plus absolute of negative 8. When R executes this command, it starts out by calculating the value of something that's more inner to the function, to the input. So first this one, right? The thing that's most on the, most inner part of the parenthesis. So it starts calculating the absolute number of negative 8. Then it sums with 1, which is 9. And then it takes the square root of 9, leading to 3. Multiple arguments or inputs. When we use stats functions, I'll tell you which arguments you will need to specify and in what order. So when I told you earlier that you would learn to modify functions, I would say to you, well, you're running this function to find the average of your variable that is inside a data set, right? The input could be that data set. So you might need to change the name of the data set from what you saw in class to what you will do in your independent activity, right? So I'll tell you, hey, use the function to calculate the mean. And here is the input that you need to put in, and in this and that order. Sometimes we do not need to specify an argument that the function actually uses, and these are called default arguments. To understand what these concepts are all about, I'll introduce another function, the round function, which can be used to round some value of the nearest to the nearest whole number. For example, I could type this: round 3.1415, the pi number. And then if you look, you see that you rounded it to 3. Default argument. Note that we gave the function round only one argument explicitly, the number we wanted R to round. The other argument it uses, which is how many decimal places to use when rounding, is implicit. It is a default argument, here set to 1. So if you say nothing, if you just use the round function and just provided one number, the number to be rounded, it will use by default, it will assume by default that the second argument is 1. Meaning round this with just one number, right? Suppose, however, I wanted to override the default value. That is, I wanted to get 3.14 as the output. Not 3, but 3.14. So I wanted to get 2 decimal places, okay, as the output. The round function supports this by allowing you to input a second named argument to the function that specifies the number of decimal places that you want to round the number to. In other words, I could do this. Round 3.1416.5, and the second input is 2, which means keep only two decimal places. And there you go. If you change to 1 decimal place, it does this. If you change to 0, it does this. So I guess the default value, that was my mistake there. Default value is 0, actually. Okay, let's go back to 2. Here it is, 3.14. In sum, what's happening here is that I've specified two arguments. The first argument is the number that needs to be rounded, and the second argument is the number of decimal places that it should be rounded to. 0 is the default, but you can have 1 or 2 or 3 or 4. And the number of arguments are separated by a comma. So every time you have multiple inputs to the function or multiple arguments, we're going to separate them with comma. Argument names. Most R functions use argument names to help you remember what they are. While this is not very useful with simple functions, it can come in handy for more complicated functions. For the round function, for example, the number that needs to be rounded is specified using the x argument. And the number of decimal points that you want it rounded to is specified using the digits argument. Because we have these names available to us, we can specify the arguments to the function by name. We do so like this. Round, x, the number to be rounded, is going to be called x, and we say that's equal to 3.1415. And here's the number of digits, meaning the number of decimal places, equals to 2. So you do not need to specify arguments by name, but when you do, you need to input them. When you do not, what's the advantage, right? Why do I want to complicate my life and actually put the names? Here's why. You don't need to, but when you do not use names, you need to input them in a particular order. If you choose to specify their names, it does not matter what order you type them in. If you don't put the names in, R will assume the first one is the number to be rounded, the second one is the number of decimal places. But you can use the names, and then you don't have to memorize the order. It's just what you prefer to memorize, I guess, which varies between all of us. Very inclusive. So round, 3, 14, 16, 5, and 2 will give you the same output as if I say x. This is the number I want to round in digits. This is the number of decimal places I want to round it to. But I can also flip the order if I use the name of the variable. I'll click go here to run this code, and you see that the answer is the same for each one of the functions. But not this one, because here I'm not naming the argument, so it's thinking that I want to round to, and that I want to use 3.14 decimal places. It basically just gives us 2 because there is no need for rounding. Okay? All right, so now let's go to exercise 3. Calculate the number of seconds in a year on the simplifying assumption that a year contains exactly 365 days. Pause the video, give yourself a little time to think, and then come back and watch me solve this. All right, here we go. Let's think about it this way. The year has 365 days. Each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. So let's do the multiplications here. So 60 seconds to form 1 minute, right? 60 minutes to form 1 hour. That's the number of seconds I have in 1 hour. But I have 24 hours a day, so I'll multiply that. And I want to know how many seconds in a year, so I'm going to multiply by 365 days, which is the number of days in a year. Simplifying assumption, but, close enough. So let's take a look. That would be the number of seconds in a year. All right, we'll break here because we're in the 15-minute mark, so you can take a break and then come back for us to continue on. All right, see you soon.